Hey folks, how's it going? It's Mr. Murray coming to you with a little video on our next topic in probability, and that has to do with independent events, dependent events, and the multiplication rule. So in this video, I'm going to walk you through what in the Integrated Math 2 textbook would be sections 23.2 and 23.3. And we're going to talk about on a very kind of like basic level what independent events and dependent events are. How does the multiplication rule fit into there? Because, right, this all ties into probability. And then we'll walk through some examples of how we solve problems using these. I've also assigned on the myhrw.com, I've assigned some practice problems for the Course 2 Honors Class 2019-2020. So please make sure you take a look at that. So what does it mean to be independent or dependent when we talk about events? And so to get us thinking about that, I'll give you an example here. So here's me, right? I'm thinking about going outside and I'm asking myself, well, I've got this umbrella, right? Because you never know when you need one, right? So, and I like to have this umbrella with me and I leave it by my door. So what I'm thinking is I take a look and it's sunny outside, right? And so what I think is, what's the probability right now that I am going to grab my umbrella and head outside? If you think about the fact it's sunny, some people will grab an umbrella to have with them just in case. But generally, it's not too good. Let me give you another scenario. Let's say that I'm in the same position, except now I see that it's raining outside. Well, now the probability that I'm going to take my umbrella with me is going to be a lot higher. So if you think about this little example, and this is just meant to be really, really oversimplified and just to kind of give you like a surface level example. But if you think about it, right, the probability that I'm going to take my umbrella before I leave depends on what the weather is outside, right? So that would be an example of a dependent event because the condition of it being rainy or sunny affects that probability. Now to contrast this, let's take a look at another scenario. So I'm about to leave and I realize that my shoes are untied. It happens to be Monday today. What's the probability that I'm going to tie my shoe given that it's Monday? Probably a pretty good probability if you think about the fact that I'm very likely to tie my shoes, right? Because I don't want to leave my house and start tripping all over the place. Now, what if we were in the same scenario, but it was Friday? Does changing the day of the week impact the probability that I'm going to tie my shoes? No, right? I'm going to be equally likely to tie my shoes, generally speaking, no matter what day of the week it is, right? Because the danger of tripping and hurting myself by not tying my shoes, well, that doesn't depend on whether it's Monday, Friday, Sunday, or Thursday. It doesn't depend on the day of the week. Okay, so these are some really oversimplified examples, but this kind of concept comes up in probability all the time. We think about how does one event impact another event? And when I think about the probability that something is going to happen, how does the fact that an event impacts another or not weigh in to how I actually calculate this probability? So independent events. Two events are said to be independent if the probability that each will occur does not depend on whether the other has already occurred. That is to say, events A and B are independent if event A happening doesn't depend on whether event B has happened, and event B happening doesn't depend on if event A has happened. For example, if we take two dice and we roll them, and I want to know what's the probability that I'm going to roll a 6. Well, if I roll a 6 on the first die, it doesn't impact the probability that I'm going to roll a 6 on the second one. So those probabilities are independent, right? The probability of rolling a 6 on one is independent from the probability of rolling a 6 on the other. Similarly, when we're working with cards, there's this concept of what's called replacement. Okay, see this idea of replacement here? So replacement is about whether you take the thing so usually we're taking something out randomly. If we put it back in, that's called replacement. If we don't, it's called without replacement. So either with or without replacement. Okay, so here's the thing. If I replace the card back into the deck, then I still have a chance to draw that card again. So here's the thing. This notion of independence is really, really important. And we have to think about, is one thing depend on another or not? This is sometimes something that we can think about in our head. Notationally speaking, what does it mean? It means that the probability of A is equal to the probability of A given that B is happening. In other words, if you do the conditional probability with respect to B, it doesn't do anything to the overall probability. And the same the other way around. And that's what it means verbally, right? The probability is the same regardless of whether B has happened. So if B has if B has happened, the probability of A remains exactly the same, and vice versa. Okay, on the other hand, dependent events are the other way around, right? Two events are said to be dependent if they are not independent, obviously, right? So this means that the probability that at least one of the events occurs depends on whether the other event has occurred, right? So in other words, the events are dependent if the conditional probability with respect to one of them, right, does not keep things the same. So for example, let's say that I'm picking people randomly for teams. If I pick this guy at random, once he's gone, the probability that I'm going to pick her randomly is now been affected, right? It's not the same as if I had taken him out and then put him back in, right? So for example, let's see. So there's 2, 4, 6, 8, 9. So originally there was a 1 in 9 chance of choosing this guy. Given that one person has been removed, there's now a 1 in 8 chance of her being chosen. So you can see the conditional probability, the conditional is not the same as the original. Here we have the notion of without replacement. And if you think about it in a card deck, if I take a card out, that's going to impact the probability that I'm going to draw the next card, right? Because now when I go to pick my second card out of the deck, there are less possible cards to choose from. So there might be a higher probability of getting the card that I want. Okay, so this is the idea, right? We have independent events and dependent events. Okay, so is it independent? That's something that we might have to figure out. So I'm going to present this to you in terms of thinking like logically, but also in terms of two-way tables, because we talked about this a while ago, but two-way tables are actually really important for some of these ideas and measuring the connection between different things. So the two-way frequency table below gives data about 180 randomly selected flights that arrive at an airport. Let's see if we can find the answers to these questions. Is the event that a flight is on time independent of the event that a flight is domestic? So what's the probability that a flight would be on time? What's the probability? So let's let event A be on time. Let's let the probability to B be that it's domestic. So the probability that a flight is on time is equal to 162 out of 180. If we were to choose randomly, there are 162 occurrences of flights being on time out of 180 randomly selected flights. Now, what's the probability that a flight is on time given that that flight is domestic? Well, look, there are 120 domestic flights, and of those, 108 are on time. So if this is independent, then conditioning it on the fact that it's domestic shouldn't matter. I should get the same answer either way. And so what they're getting at is, does it matter if the flight is domestic or international? Will I have the same amount of on time versus late either way? So when I do 162 out of 180, what I get is 90%. And I guess I shouldn't do 0.90%. I should do 90%. I had a decimal originally. When I do 108 out of 120, I also get 90%. So therefore, the probability that a flight is on time is equal to the probability that it's on time given the flight it's domestic, the fact the flight is domestic. So these things are independent. Okay, part B. Is the event that a flight is international independent of the event that a flight arrives late? So does one thing relate to the other? So let's take a look. So, and if you think about it, is one thing causing the probability of the other to change? That's an interesting question. So what's the probability? Let's let C be the event that we're international. Okay, let D be the probability that we are late. So what we need to look at is this. The probability that a flight is international is given by the fact that there are 60 international flights out of 180, and the probability that a flight is international given that it is late. Well, how many flights are late? There are 18 flights that are late. There are 6 flights that are international. By looking at it, we can already see by simplifying, you get 1/3 and 1/3. So these are equal. Now, technically, you should do it the other way around. The probability that you're late is going to be 18 out of 180. What about the probability that you're late given that you're an international flight? So out of the 60 international flights, 6 of them were late. And I do realize, yes, I know I do need to flip these around. But unfortunately, Smart Notebook has decided to stick those all together. So here you can see you simplify, you get 1/10. 18 and 180, you simplify, and you get 1/10. Okay, so you can see that in either case, the fact that one of the events happens has no impact on the probability. It was 1/3 beforehand. Given that the event has happened, it's still 1/3. It was 1/10 beforehand. Given the fact that the event has happened, it's still 1/10. So therefore, yes, they must be independent. Okay. Lastly, this two-way frequency table shows data for 80 randomly selected people who live in a metropolitan area. Is the event that a person prefers public transportation independent of the event that a person lives in the city? So again, let's define our events. Let's let A be equal to prefer public transportation, and B is lives in the city. So what's the probability that a randomly selected person prefers public transportation? Well, there are 35 people that prefer public transportation, and there are 80 people who were sampled, so that's that. Now, what's the probability that someone prefers public transportation given that they live in the city? If the fact they live in the city has no impact on the fact they prefer public transportation, then this probability should be equal, and that would tell us that they were independent, at least that direction. So there are 36 people who live in the city, And of those 36 people, 24 prefer public transportation. Okay, so that's interesting. Well, this is 2/3. This one here, yikes, 35 out of 80. This is definitely not 2/3. This is actually not even, this is closer to, if I do 35 out of 80, let's actually see if I can 2-frac that. So we take this and 7/16. I probably could have done that faster if I just done like that. So these things are clearly not equal to each other. So that already tells us that they are dependent. Now, you could verify it the other way around. What's the probability that someone lives in the city? Well, how many people live in the city? 36 out of 80. Okay, so 36 out of 80 is 9/20. Now, what's the probability that they live in the city, given that they prefer public transportation? If public transportation preference has nothing to do with whether they live in the city, then this should have no effect. We should get the same probability. So how many people prefer public transportation? 35 do. Of those, 24 live in the city. This is actually not even reducible. So these are, we can also see that these are not the same either. So neither of these are the same. These events are dependent on one another. Okay, because the fact that one has occurred does have an effect on the probability. We go from 7/16 to 2/3. We go from 9/20 to 24/35. So folks, please make sure you understood this one, because this was a really important idea. And then when you're ready, you can go ahead and we'll move on to the next page. So folks, here's what it comes down to. Here's kind of like the big enchilada, so to speak. This is what we call the multiplication rule. The multiplication rule tells us the probability that 2, and actually this extends beyond 2. So actually 2 or more. But so if we have, let's start with 2. So if we have 2 events, to find the probability that both of them will occur, right? If they're independent, you simply take their individual probabilities and you multiply them by each other. So the probability that A and B both occur, if independent, is the probability that A occurs times the probability that B occurs. If the events are dependent, then it's a little bit different. It's the probability that A occurs times the probability that B occurs, given that A has already occurred. Now, technically, it always follows this rule. But remember, if they're independent, the probability that B has occurred, given that A has occurred, is the same thing as the probability that B has occurred, because the events are independent. Okay, so this is what it's saying. If I ever ask, what's the probability that this happens and this happens and this happens, any number of things, you just take their individual probabilities, you figure them out, and you multiply them together for the final answer. And believe me, we'll do plenty of practice in this video. The main difference is, if they're independent, you only focus on one thing at a time. And if they're dependent, you have to consider the impact of any previous events. Okay, so again, we'll have plenty of examples, and we're actually going to jump into one right now with the probability of independent events. So in this example, I'm going to throw 2 dice. Now, dice are independent because what you throw on the first dice the first die has no impact on what comes up on the second one, right? We're assuming like they don't collide or anything. We just throw them and we see what we see on the top. Okay. So suppose we have two events, A, which is rolling 5 on the first die, and B, which is rolling 3 on the second die. What's the probability that both events occur? That is, what's the probability that A, we roll 5 on the first die, and B, we roll 3 on the second die? Well, if you look at this, this is a table of all possible combinations. You can see there's only one where we roll 5 on the first and 3 on the second. So there's one combination that works. That's what we want. And there are 36, 1, 2, 3, 4, 5, 6 times 1, 2, 3, 4, 5, 6 possible combinations. Now, interestingly, notice how for any given die, you have a 1 in 6 chance of getting a 5. And for any given die, you have a 1 in 6 chance of rolling a 3. And observe how 1/6 times a 6th is equal to 36. So what we can do, instead of making this table, because these are independent events, we can say, wait a minute, what's the probability of rolling a 5? 1 out of 6. What's the probability of rolling a 3? 1 out of 6. Because they're independent, I know I need to just take those sixths and multiply them together. Alrighty, folks, so here's a little example of independent events. So a jar contains marbles of various colors as listed in the table here. I've calculated the marbles quantity ahead of time. I know there are 60 total marbles. Suppose I kind of cover my eyes and I just put my hand in and randomly draw one marble from the jar. Okay, I make a note of it, and then I put the marble back into the jar. And this concept is called replacement. Remember, this is called with replacement. I then randomly draw a second marble. Use this information to answer the questions, giving a probability as a percent and rounding to the nearest tenth of a percent when necessary. So this is an independent event. And why? The reason is because every time I stick my hand in that bag of marbles, because I'm replacing each time I take a marble out, I always have the exact same number of marbles in the exact same quantities of red, yellow, green, and blue. So the fact that I've taken out a marble previously has no impact on the probability that I'll take out a marble in the future. So that is to say, in this example 5, what is the probability that I draw a blue marble first and a red marble second? The fact that I've gone in and drawn a blue marble has no impact on my probability to draw a red marble because the blue marble is put back, meaning I stay always 20, 18, 12, and 10 for a total of 60 marbles. So to do this, we first need to calculate the probability that I'm going to draw a blue marble. There are 10 blue marbles in the bag and 60 blue marbles total. The probability of drawing a red marble, there's 12 red marbles in the bag, or 20 red marbles in the bag rather, and 60 marbles total. And so this is my overall probability, okay, using the multiplication rule. So I multiply across the top, I get 200. I multiply across the bottom, I get 3,600. The hundreds cancel. I get 2 over 36, which is 1 over 18. And I will now do 1 over 18 on my calculator. And I was told to round to the I need it as a percent, round to the nearest tenth. And that would be 5.6 approximately percent. All right. What is the probability that you draw a yellow marble first and a green marble second? So the probability to draw a yellow marble 18 over 60. The probability to draw a green marble, 12 over 60 because the marble was put back. So I'll do a little bit of simplification here. So I'll start with 18 over 60. I can already see 18 over 60 looks like it can be simplified. And it can, because 18 over 60 is equal to 3/10. 12 over 60 is equal to 2/10. So this is equal to, I think I can clean this up even more. This is actually 2/10. Do better than that. Matter of fact, I can make that 1/5. So we get 3/50ths, which is 6%. So 6% chance. Okay, so you're just taking the probability of the first, multiplying by the probability of the second, because they're independent events. Now remember, you're always multiplying by the probability of the second given the first, but if they're independent events given the first, right, remember it has no impact. Alright, probability that I draw a yellow marble both times would be 18 out of 60 to draw a yellow times 18 out of 60. Because remember, since you put the yellow marble back, there's still always 18 yellow marbles in the bag. And so that's 3/10 times 3/10, which is 9/100ths, which is 9%. Okay? What color marble for the first draw and what color marble for the second draw have the greatest probability of occurring together? This is a challenging one. What color marble for the first draw and what color marble for the second draw have the greatest probability of occurring together? So basically, we want to think about how are we going to get the biggest possible probability out of this, right? And so I would say that the greatest probability comes from the greatest probability in each individual choice, right? So what's the best I can do for the first one? Well, the best I can do is red. Now remember, once I take a red marble and I put it back in the bag, I have no better chance of grabbing another red. You know what I mean? Like, I could grab a second red. In fact, I've got a better chance of grabbing a red second than I do of grabbing a yellow second, because the fact that I took a red out has no influence on the probability that of the second marble that's grabbed, essentially. So I would argue, if you look at the red, I have a 20 and 60 chance of grabbing a red, and I have a 20 and 60 chance of grabbing a second red, and that is a 1/3 times 1/3. I have a 1 in 9 chance of grabbing 2 reds. Okay, it's unlikely to get any better than that. Whereas with blues, if you look at grabbing 2 blues by comparison, that would be 10/60ths times 10/60ths, which would be a 6 times a 6th, which would be 1/36. Okay, so this is 4 times more likely to happen. So I would argue the color marble most likely red and red, and the probability that's going to happen is 1/9 or about 11%. If you look at 1/9 on your calculator, you should get 11 point, or if you could do 11.1 if they want you to round to the nearest tenth. So please make sure you understood what I did there, and rewind and kind of go back through if needed, anything you need to do. And then when you're ready, I'll go ahead and move on to the next problem. This is another kind of common problem, and this is the one that has to do with a spinner. Now, a spinner is also considered independent because what you spin on a particular round has nothing to do with what you're going to spin on the next round, right? You just spin the number and you see where it lands. The pieces are what they are. You never move the pieces. You keep the pieces fixed and you spin and spin and spin, okay? So, what's the probability that a spinner stops on 1 first and 2 second? So what's the probability? Well, remember, also I just wanted to note we're going to do the same thing, by the way, with our answers. Percents, nearest tenth when necessary. But I'm going to do fractions as well. Okay? Now, given that each, by the way, section of the spinner is the same size, that means we just have to focus on the number of them in there. So there are 1, 2, 3, 4, 5, 6. There's 12 sections total. So the probability that I stop on a 1, assuming that it's going to be completely random, is 1, 2, 3, 4 out of 12. And then the probability I'm going to stop on 2 seconds. Well, what's the probability I'm going to do 2? Well, how many 2s are there? There are 1, 2, 3 2s. So 3 out of 12. So 4 out of 12 times 3 out of 12 is equal to 12 out of 144, or 1 out of 12. Okay, and 1 out of 12 is equal to approximately 8.3%. Okay? What's the probability that a spinner stops on 4 first and 3 second? Well, 4. How many 4s are there? 1, 2. There are 2 4s. And there are 12 total options for it to land on. In terms of 3s, there are 2 possible 3s and 12 total options to land on. So that leaves us with 4 out of 144, which is equal to 1, because I can divide by 4 because these end in 44. So the last 2 digits are divisible by 4. So the whole thing is, so it goes into 12 3 times, and then it goes into the remainder 6 times. So 1 out of 36, or 2.8%. And we would expect the probability to be lower because if you think about it, you have a higher probability of getting a 1 and then a 2, given the fact that there are more you got a greater probability of getting a 1 and a greater probability of getting a 2 than you do of getting a 4 and a 3. What's the probability that the spinner stops on an odd number first and then an even number second? Well, what are the odds? So we better what are the odd numbers? So how many? So let's just do a quick tabulation. We have how many 1s? We have 4 1s. We have 3 2s. We have 2 3s. And we have 2 4s. 4, 7, 8, 9. I think I may have missed one. Oh, but nope, because we do have a 5 as well. So 4, 7, 8, 9, 10, 11, 12. So odd number first, even number second. So odds 4, 5, 6, 7. So we have a 7 in 12 chance of landing on an odd. And then I believe we should have a 5 in 12 chance of landing on an even. So it gives us 35 out of 144. Do that on my calculator. I get 24, about 24.3%. 24.3%. And finally, what first number and what second number have the least probability of occurring? So what I'm going to look at is, now, could you repeat? Technically, you could get the same number both times. So this one's tough to read this question thoroughly. I would say 1 and I would say rather 5 and 5 is the least, with a probability of 1 out of 144, because since 5 occurs the least number of times, 5 showing up twice is 1 out of 12 times 1 out of 12, and that's the smallest possible 2 different things you can put together. So I would say 5 and 5, assuming you're allowed the same number twice, and you get a 1 out of 12 and 1 out of 12, because each time that's the probability. for 1 out of 144, or 0.7%. Okay, so less than 1% chance. All right, now lastly, we're going to talk about dependent events and how to calculate the probability of that. Dependent events are almost exactly the same as independent events, but you just have to remember that once you get to the part where you have to calculate the second thing, something's happened that's changed the calculations a little bit, okay? So let me give you an example. Let's say that I put my hand into this jar, and I'm going to pick a random marble out of this jar. So if I'm going to pick a random marble out of this jar, right, what's the probability that I need to pick a yellow first and a red second? So the probability that I pick a yellow is 1 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have a 1 in 10 chance of picking a yellow. Now, once I remove the yellow, there are only 9 marbles left, and out of those marbles, one of them is a red. So this would be like PA, and this would be probability that B happens given that A has already happened, right? The probability that you're going to pick a red marble given that you've already taken out one of the marbles when you picked the yellow one out. So what the result would be is this would be 1 out of 90, and that would be a little bit more than 1%. I don't know if it would even round up to 2. Yeah, it'd be like 1.1%. Okay? So here's the thing. You just have to be aware of the fact that now instead of them being 1 out of 10 and 1 out of 10, it's 1 out of 10 and 1 out of 9. Because again, the fact that we pulled out a yellow marble reduced the number of marbles in the bag and therefore increased the chance that we would pick out a red. Let's see how we actually do some of these. So a bag contains tiles with the letters shown at the right. Find the probability for randomly drawing tiles one after another without replacing them. Even when there's 3 things, it's not going to matter, because if you want probability of A and B and C, all of them happening. So first, you got the probability that A happens. Then you add the probability that B has happened, given that A has happened. And then you have the probability that C has happened, given that B has happened, given that A happens, if that makes sense. Okay, so let's just take a look one at a time. And by the way, you shouldn't be adding. My apologies. You should be multiplying. So, what's the probability that we choose A? There are, first of all, 12 tiles. I'm just going to leave these as fractions because I've got the freedom to do that. 3 of them are A's. So I have a 3 in 12 chance of drawing an A. Once I pick out an A, that's gone. Now there's only 11 tiles. Because notice, without replacing, now there's only 11 tiles. Of those 11, 2 of them are B's. So I have 6 out of 132. And you could simplify 6 out of 132 if you wanted to. Your calculator could give you a little cheat code there, and that would actually be 1 out of 22. Okay? All right. Now reset it. We reset. We're going to assume between problems. So C and then E. So I have a 2 in 12 chance of drawing a C. Once I draw a C, one of them has been removed. So only 11 remain. And out of that, I've got a 1, because there's one E, chance of drawing an E. So that's 2 out of 132, which is 1 out of 66. B and then D. Okay, so now I'm going to draw out a B. There are 2 B's, so I have a 2 out of 12 chance of drawing a B. Now 1 is removed, so there's 11 left. I have a 1 in 11 chance of drawing D, because there's 11 letters, one of them has the letter D on it. So that also is 2 out of 132, which is 1 out of 66. Okay, E, then C, then B. So I've got a 1 in 12 chance of drawing an E. Now the E is gone, so there's only 11 left in the bag. I have a 2 in 11 chance of drawing a C. Now I've just drawn a C, so the C is gone. So now there's only 10 tiles left, and I draw 2 out of 10 chance of drawing a B. So that's what I'm getting at with the givens. Given that you've drawn 1, there's only 11 left. Given that you've drawn 2, there's only 10 left. Okay, hopefully that makes sense. Okay, next thing we have to do is we have to calculate things out. So I have got 1, 3, 2, 0 over 4. And I know the bottom is divisible by 20, or divisible by 4 rather, because of the 20. So I get 1. It should be 330. I'm just going to confirm that on my calculator. Yes, it is. So you got a 1 in 330 chance of that. And that makes sense, right? Because 1, there's a lot of things to choose from, but the more things that have to happen for this to all work out, right? E has to happen, and then specifically C has to come next, and then specifically B has to come third, right? The more of those you add on, and if you say all of those must happen, right, the less likely that's going to be true. All right, D then A then A. So D, I've got a 1 in 12 chance. 1's removed, so 11 are left, and I've got 3 A's. Now here's where it gets tricky. So 1 is left, so I have 10 left, but I've also removed an A, right? So I remove an A, and I removed D. So now there's only 2 A's left out of 10, because if 1 A has been taken out, there's only 2 remaining to choose. So that's where it gets tricky, right? Ordinarily, we just do however many were in the bag, right? But now remember, you had to take one of them out when you picked out the second one, so you have to take that into account when you're doing these calculations. And I know that 1320 is divisible by 6. And so I get 1 out of 220. So you have a greater chance of choosing a D and 2 A's than an E, a C, and then a B. All right, last set of problems here. There are 3 apples, 4 oranges, and a pear in a bag. Determine each probability. So first, the probability that you select an orange and then a pear at random without replacement. So you're not putting them back. So the probability you select an orange, that would be 4 out of 3, 7, 8. Times the probability that you select a pear, given that you've already selected an orange. So the fact that you've selected an orange reduces the bag size to 7, and then one of those 7 is a pear. So you get 4 out of 8, and actually we'll simplify that to 1/2, and then this becomes 1/14. Okay, you select an apple and then a pear at random. So first I reach in, I get a 3/8 chance to get an apple. Given that the apple has been selected, there are only 7 pieces of fruit left, of which 1 is a pear. So it gets me 3 over 56. 5 plus 6 is not a multiple of 3, so I'm going to have to leave it. You select an orange. So you select an orange. There's a 4 out of 8 or 1 out of 2 chance to select an orange. Then you select an apple. So given that you've already selected an orange, there are only 7 pieces of fruit left in the bag, of which 3 of them are apples. And then a pear, well, now that you've selected an apple and a pear and an orange, there are only 6 pieces of fruit left, of which one is a pear. So that's how you think about it. You got to just break it down step by step and really have an analytical mind. The probability stuff is not easy, I know. So you get 3 out of 84, and 3 out of 84 actually can be simplified to 1 out of 28. Lastly, you select an apple, an orange, and another apple without replacement. So the probability select an apple, you have a 3/8 chance to select an apple. Now, 1 piece of fruit is gone, given that you selected an apple, so 7 are left, out of which 4 are oranges. Now, given that you've already selected an orange and an apple, there are only 6 pieces of fruit gone, or remaining rather. But because you've taken an apple already, only 2 of those are apples. So I got 3 times 4 times 2, which is 24, over 8 times 7 times 6, which is 336. And what I'm going to do is I'm going to go ahead and convert that to a fraction. And when I do that, I get 1/14. All right. So folks, in this video, to sum up, what we talked about is independent events and dependent events. An independent event, or 2 independent events, are events that do not depend on each other to occur. That is to say, they are equally likely to occur regardless of whether the other one has already occurred. So we talked about rolling dice, and we talked about anything that involves replacement. When you put something back, you keep all the proportions the same, so the chance that the next event will occur is equally likely as it was before. Dependent events are events that rely on each other somehow, or events that influence each other. So for example, if I'm picking people for a sports team randomly, once I've picked one, there are less people to choose from, and so the fact that one has already been chosen affects the probability. Okay, and then we also talked about without replacement, like a card deck, the fact that I take one card out of the deck means that I'm more likely to pick other cards in the deck. We introduced then the multiplication rule. That's one of the other big things we did. We did talk about how to confirm if it's independent, but the main other big thing we talked about was the multiplication rule. And the multiplication rule says if I want to find the probability that 2 or more events has occurred, I just take each of the probabilities and I'm going to string them together in a series of multiplications. If the events are independent, I just take the individual probability that A happens and I multiply it by the probability that B happens. Okay, and if there were 3 events, A, B, and C, and they were independent, it would be the probability of A times the probability of B times the probability of C. And then if the events are dependent, you just have to take into account, as you do each multiplication, the fact that previous events have already occurred. And if the events are independent, you can expect that that will have some value on the probability, because by definition, that's what it means to be dependent. All right, so please make sure you do take a look at the MyHRW assignment on independent and dependent events and the multiplication rule. Keep the questions coming. I'm looking forward to a great wrap-up of probability and moving on to our last main unit of the year. Best of luck. Don't forget to love math. And remember, you can do it. Thanks again for watching. Feel free to like and subscribe to get my latest videos, and have a wonderful day.